but the good thing about concentric heat exchanger is that it's quite cheap. Therefore, if you go to the mills, small mills that process CPO, uh, rope oil palm, you will see that they are using concentric tube heat exchangers. And another one, the second one, would be the shell and tube heat exchangers. So shell and tube heat exchangers are the one that mostly used in industry. So later on, you're going to see, if you're graduated, after you have graduated and you venture into your career as a chemical engineers, you will see a lot of shell and tube heat exchangers. The reason why is that because it's quite efficient, and also the heat recovery or heat energy that's used are quite efficient compared to the other heat exchangers. And the last one would be the compact heat exchangers. The compact heat exchangers, we also actually have several types of compact heat exchangers. Um, we have plate and frame heat exchangers. So plate and frame heat exchangers, you are going to learn in not learn, but you are going to use in your experiment in your third year later on. So plate and frame heat exchangers, spiral heat exchangers, plate fin heat exchangers, and printed circuit heat exchangers. So as we move down from 1 to 4, the cost of these heat exchangers would increase. So in order for you to use the printed circuit heat exchanger, you must have a good reason for it. Usually, we only use printed circuit heat exchangers for oil and gas industries because the cost is very super high. One printed circuit heat exchanger would cost around at least 1.5 million ringgit. So that's why we don't really use printed circuit heat exchangers. However, the good thing about printed circuit heat exchanger is that it's very small. So since we have space limitation on a platform rig, therefore we usually use printed circuit heat exchangers. I'm going to show you a video here where they show how they are going to produce uh, printed heat exchangers. I'm going to share this here. Okay. I need to present on screen again.
Doctor,
Yeah. Can you?
we can't hear the voice of the video, the sound of
Oh,
the
really?
video.
Okay.
Yeah, it's
Okay.
very,
It's what? Sorry?
the volume is very low. Maybe if you can try to increase the volume of the.
This is already. Uh, Let me check. Maybe it's
Oh,
because of this. Yeah. Is it possible if I
Yes,
replay it
doctor.
again? Is it
Yes, yes.
okay?
We
Yeah.
would like to.
Yeah. Okay. Sorry about that.
Now, let's look at the construction of the Heatrip exchanger. A Heatrip exchanger is constructed from flat metal plates into which fluid flow channels are chemically etched. These fluid flow channels are typically 2 millimeters wide and 1 millimeter deep semicircles. The plate layout and flow patterns for the cold and hot sides of the exchanger are designed to suit the particular duty. Each exchanger is uniquely designed to offer an optimized balance between the heat transfer, pressure drop, thermal effectiveness, and mechanical requirements. The etched plates are then stacked alternately, cold, then hot, and diffusion bonded together. Diffusion bonding is a solid-state joining process where, under high temperature and pressure, grain growth takes place at the interface of two metal surfaces in contact with each other. The resulting bond achieves the same mechanical strength as the original material. The diffusion bonding process does not employ any braze, flux, or gaskets in the construction of the heat exchanger core. This bonded core behaves as a single metal block with engineered holes running through it. It can then be machined and welded using conventional fabrication techniques. In order to achieve the performance, a number of blocks may be required. These individual blocks are then welded together to form an exchanger core of the required capacity. In order to confirm the absence of pressure between each block, an interblock vent is created in the block-to-block weld. Once the core is complete, headers, including prefabricated nozzles, are attached. These are half cylinders which distribute fluids into the exchanger core. The exchanger is connected to the customer's process piping by way of nozzles. The nozzles can be designed to meet the customer's individual requirements and typically use flanges, compact hubs, or weld preparations. Supports are then attached to the exchanger. The most widely used method is the N-type support. These are welded to the ends of the exchanger core. Alternatively, saddle-type supports can be fitted to the lower handle of the exchanger. Lifting lugs are typically located at each end of the exchanger and are suitable for fitting with D-shackles for the attachment of lifting screws and chains. The lifting points can be incorporated into the N-type supports. Finally, the exchanger can be externally protected by painting or by sheathing with a corrosion-resistant material. This sheathing is a sheet metal cladding that is applied to the outer surface of stainless steel cores for enhanced protection in marine environments, typical of offshore installations. Heatrip exchangers are fabricated mainly from stainless steel, but can be made from other materials. Heatrip held both an ASME-U stamp and an ASME-R stamp, and operate an integrated management system which is certified by Lloyd's Register and which encompasses ISO 9001, ISO 14002, and OSAS 18001.
Right. So this would be an example of a compact printed circuit heat exchanger, and this cost, as I said before, it costs around at least 1.5 million. So it's quite expensive, and in normal factories or plant, oleochemical plants, we don't really use this particular type of heat exchanger. However, we use plate and frame heat exchangers, spiral heat exchangers, and also plate and fin heat exchangers. But we don't really use printed circuit on for normal factories. So let's say that you are going to offshore or platform later on. Please don't be surprised if the heat exchanger is quite small. It's very small because we have space limitation. So that's why they use printed circuit heat exchanger. And another thing, if I can remember, if I'm not mistaken, there is one portion or one slide where I mentioned that inside of the tube, if I'm not mistaken, is it tubes? I think it tubes. Yes. Inside of the tube, sometime in order for to enhance the heat transfer on either both side of the tube wall, we use corrugated. So corrugated is when you have wires or twisted wires installed inside the tube. So I'm going to show you that particular. So we have this one. I think I have shown you previously, but it's a good example. So for example, if we have tubes installed in the heat exchanger, in the shell and tube heat exchangers, one way of increasing the tube, the heat flux inside of the tube would be to use a corrugated tube. So you can have it inside of the tube to enhance the heat flux inside of the tube, and you may put it outside of the tube to enhance the heat flux outside of the tube. So it's up depending to what you wanted to increase the heat flux. So I'm going to show you, if we have a smooth tube, what happens. So this is a smooth tube, and this would be a corrugated tube. So as you can see that, please bear this in mind, because I always have but I always have your seniors in your fourth year and also in your third year will always ask me regarding this. Which one is better, turbulent or laminar? In heat exchanger, also in reaction, later on, I'm not really sure whether you already done your reaction, but in reaction and heat exchanger, generally in chemical engineering, we wanted to have a turbulent flow, because if we have a turbulent flow, what happens is that all the mixing is happening. As you can see here, if you have if this is our velocity profile. So if we try to do a velocity profile, if we have a laminar flow, for example, this one, the left hand side is the laminar flow, you will see that there is red zone, deep red zone. So that deep red zone we call as dead zone, and we don't want a dead zone in our equipment. The reason why we don't want a dead zone in our equipment is that because if we have a dead zone, the mixing will not be rigorous and enhanced, and some of the substance will not be able to mix together. So we don't have a good mixing, and some of the substance will fix themselves to the wall of the tube, and in time we can have falling. So that's why, and we need to be clean. So that's why we need to have a turbulence flow. So this is a turbulence flow. As you can see that we can have a we have a uniform, what do you call it, a mixing. As you can see that on your right hand side, the velocity profile is almost the same, the color is almost the same compared to the left hand side. So that's why we wanted to have a turbulent flow. And as you can see, the mixing is quite rigorous, and that's what we wanted. Otherwise, your pipe will be full, and you need to clean your pipe rigorously, or you need to clean your pipe every month. So that's not a good thing for your process. So as you can see, there's a lot of mixing inside the turbulent flow. So that's what we wanted. That's why we wanted turbulence flow. So later on, if your supervisor asks you which one is better, laminar or turbulence, so you need to say that you in term of heat transfer, you would want to have turbulence, because if you have a turbulence flow, therefore the heat flux would be higher and there will be more energy transfer. So that's the thing that you need to keep in mind. So that would be the video. Right. So after that, you need, okay, so this is an example of shell and tube. So shell and tube are quite common in our industry. You will look at it most of the time if you're working as a chemical engineer later on, and as usually you're not going to fabricate it. We are going to buy it from several companies. One of the company that quite popular in Malaysia, Alfa Laval. That's quite cheap compared if you go to Hill or any other technique. So Alfa Laval quite cheap, and usually they deliver the same thing that the international company give you, shell and tube heat exchanger. So this is a fabrication of shell and tube heat exchanger. I have one student, my ex student, your senior, who's working in Alfa Laval, and his job is to design heat exchanger, and he liked it so much. He enjoy designing heat exchanger. He also do some other things, but most of the time he would do designing heat exchanger, because heat exchanger is quite straightforward. It doesn't really have you don't have to calculate the reaction and so on. You only need to calculate the value of Q and also thickness. So it's quite straightforward. And as you can see here, this would be a typical shell and tube heat exchanger. So here you have two ends. So two ends here. This we call as channel. So channel, it's actually adhere to TIMA, what we call it. I just show you. I'm not really sure whether I've given you this. I think this would be TIMA designation for shell and tube heat exchanger. I think I need to upload this on Spectrum for you to see. So if we refer back to this particular heat exchanger, the design of heat exchanger is actually where is it? Okay, sorry, it's actually governed by TIMA. TIMA is Thermal Engineers Manufacturing Association, if I'm not mistaken. And it's, for example, if we have, it's governed, usually shell and tube governed by the 3-letter So for example, I'm being asked to design I cannot really, okay. So please design, my supervisor would say to me, okay, Mahar, please design B, uh, so BH and BHNU. So they will say, okay, Mahar, please design this BHU shell and tube heat exchanger with the specification of this. So BHU designation is referring to the TEMA designation for shell and tube heat exchanger. So B, the first letter, is actually represent the stationary head type, whether it's a bonnet, whether it's a removable channel, cover, or so on. Let's try to increase. Cannot really increase this. That's okay. So it actually refer to the bonnet integral cover. And then it asks B, H. So H here, in the middle letter, actually represent the shell type. What kind of shell that my supervisor asked me to design. So H here is a double split flow. Double split flow is a bit not that common. Usually we use one shell pass or two shell pass, but not really a split flow. But here, however, in this particular example, he asked me to do H. And the third letter actually represent the rear head type. So he asked me to design a U-tube bundle for you. So this would be the designation of that particular TEMA. So if, let's say, your supervisor asks you to do something with 3-letter shell and tube heat exchanger, please do not be surprised and uh, and tell him that you never learn about this. Actually, this is not in your syllabus, but I think this would be helpful for you later on to know about the TEMA designation and so on, because it was helpful for me. So I think you better know, you should know about this. Okay, right. So we have the TEMA designation for shell and tube heat exchanger. That's how we actually fabricate or characterize shell and tube heat exchanger. I think you need to read one by one the slide, because it's quite important for you to know about this. And also, at the end of the slide, I have given you several examples. So this is quite easy. One or two, if I'm not mistaken, one of your exam question would be referring to the design of heat exchangers. So if I'm not mistaken, it would consist the an example that relates to LMTD and also NTU effectiveness method. So in this lecture, I have shown you, actually I just wanted to tell you, okay, there are two ways of designing heat exchanger. The first one would be using the LMTD method, and the second one would be using the NTU effectiveness method. Both methods are actually the same, not the same, but in a way they are quite efficient and straightforward. However, the downside of LMTD is that in order for us to use the LMTD, we need to know all the temperatures. For example, we are going to have 2 streams. So if we have 2 streams, we need to know all the inlet and also outlet or temperature of the stream. For example, if the red color stream is a hot stream, so we need to know the temperature inlet of the hot stream and the temperature outlet of the hot stream, and also we need to know the temperature inlet of the cold stream and also temperature outlet of the cold stream. So this is the only way that we can use LMTD, because if you refer back to the LMTD equation, the LMTD equation just, it says that you need to know, you need to calculate. So delta T LMTD is actually delta T1 minus delta T2 divided by ln delta T1 over delta T2. So delta T1 and delta T2 actually correspond to a graph. Later on, I'm going to show you. So in order for us to get the delta LMTD, we need to know all the temperatures inside of that heat exchangers. However, what happens if we only know 2 of the 4 temperatures? Therefore, we need to use the NTU effectiveness. So in this lecture, I have in the previous lecture, I have introduced to the LMTD, and tomorrow I'm going to show you how to use the NTU effectiveness. For example number 1, this is quite straightforward. I'm going to show you. Right, so for example 1, it says that you need to get the value of the area for that particular heat exchanger, and also the value of the mass flow rate of the hot stream. So before we do anything, we need to draw the schematic. So this would be our schematic. This is our shell and tube. So inlet for the shell side we call as TH in, and since this is a single pass, therefore we only have one direction, TH out of the, and also we are going to have a cold stream, double pass cold stream, due to the fact that we're going to have a 2 direction. So the first direction, the second direction, therefore we call it as a double pass tube, double tube passes. So this one would be TCI, inlet, cold stream inlet, cold stream outlet. And also the most important thing that you need to remember, that you need to show the graph, the temperature graph. So this would be the temperature graph. And on the x-axis, it would be referring to the location, so 1 and 2. And the second, the y-axis would refer to T, temperature. So first, we're going to see that for the cold stream, it's actually cold stream, so it says that the working fluid of the power cycle is evaporated in the tubes of the heat exchanger and at the phase change temperature of 290. So meaning that we are going to see that particular cold stream as evaporating liquid or evaporating fluid. So we are going to see that the temperature would be constant. So this would be T TCI equals to TC out, which is equals 290 Kelvin. And the hot fluid here would be water, the seawater. So seawater, what happened is that we're going to have the seawater cool to 290. So T seawater in at 300 Kelvin, and it's going to be cooled down to C TC out at 292 Kelvin. So this would be our temperature. So as you can see that for LMTD, we need to know what is the value of delta T1 and delta T2. So this is delta T1. And this would be delta T2. So delta T1 is actually 300 Kelvin minus 290 Kelvin. And delta T2 is actually 292 minus 290 Kelvin. It would be a bit tricky if you don't show or you don't draw this graph. So that's why it's better if you show and draw this graph. And another thing we need to do is you need to do assumptions. So these assumptions, in this question, we assume that negligible heat loss, meaning that all the heat inside of the heat exchanger is transferred from the hot stream to the cold stream. So there will be no negligible loss, just put negligible loss, heat loss to the surrounding. And we are going to assume that there is negligible kinetic and potential energy. And the third assumption would be constant properties. Right, if we refer back to the question, it says that the efficiency is 3% and the power cycle is to generate 2 megawatt. So this is a very bad heat exchanger because the efficiency is around 3%. Usually we have quite a higher percentage of efficiency. Right, so first thing, we're going to calculate the rate of heat that's transferred. It says that in order for us to deliver 2 megawatts of power, we need to use a heat transfer of Q. So if you refer back to the slide, the work that the power that produced is over, the efficiency is equals to the power that produced over the heat, the rate of heat transferred. So in a way, we already know that the value, we already know the value of W, and we already know the value of now, which is the efficiency. Therefore, Q is 2 megawatt over 0.03 equal to 66.7 megawatt. So this is a very bad heat exchanger. You need to have a 66.7 megawatt of heat in order to generate 2 megawatts of energy. So this is a very bad heat exchanger. 66.7 megawatt is if I'm not mistaken, is nearly the same the power that needed for the state of Perlis. So this is a very quite high energy. And next, we need to know or to calculate the delta T, the LMTD. So delta T LMTD is delta T1 minus delta T2 over ln delta T1 over delta T2. So if you substitute everything inside this equation, you will get around 5 Kelvin. It doesn't matter because this is delta, so this is also equals to 5 degrees Celsius. Right, after that, we need to get the value of A. So if you remember for a shell and tube, the value of Q is equals to U A times F. So F here is the correction factor of the shell and tube times the delta LMTD. So in order for us to get the F, we need to refer to the previous graph. So before, okay, so we go to 11. Okay, so this would be the graph. So this is all the graphs here correspond to the types of heat exchanger. So we have several types of heat exchanger, but in this particular, the first one, this one is referring to corresponding to single shell pass and double tube passes. So we are going to use this. So if we refer back to the graph, there are two parameters that we need to get the value of F to evaluate. The first one would be P and also R. So P is actually, if you refer, it's actually 290 minus 290 over 300 minus 292. So how do I get these values actually? So if we refer back here, this is lower capital letter of T, naught minus Ti. Lower capital means that it's a cold stream, and sorry, not lower capital, but lowercase of T means that it's a cold stream, while the capital of capitals letter mean it's a hot stream. So from there, we will see that Ti, so this is actually Ti. It's actually, if we try to do, to calculate, this would be 0. So P would be equals to 0. And R here is actually Ti, just what? So this would be 300 minus 292 over 292 minus 220. So you will get nearly to infinity because the bottom part is 0. Would be 0. So you will get infinity. So if we refer to the graph here, if we have P is equals to 0 and R equals to infinity, you will see that infinity would be, so your graph, even though there is no curve that represents infinity, that's it. But since we know that as it approaches a higher number of R, it will be closer to the y-axis. So we are going to assume that it would be around here, nearly to the y-axis. And also it says that P is equals to 0. So P is equals to 0 correspond to, so R is correspond to the curves and P correspond to the x-axis. So it would be around here. So this actually correspond to the value of 1. So we will get F nearly or equals to 1. So from there, so from the graph, F would be equals to 1. And from this particular term, we can get the value of A. So A here is Q over U F delta T Lm. And we can get the value 6.67 times 10 to the power of 7. This is a megawatt times 120, 1200 watt per meter squared per Kelvin. So since F is 1 times 5 Kelvin, the LMTD, so we will get around 11,100 meters squared. So this would be your the value of the area. And the second part that we need to know would be the value of M, the flow rate. So the flow rate here, it gives, so Q here equals mCp delta TH, because we wanted to know the water flow rate. So water flow rate here is the hot side from 300 to 220 at 92 Kelvin. And we need to know what is the value of Cp at the mean temperature of the water. So Cp at Tm. So Tm here is actually the average of 300 plus 300 and 292 Kelvin. So it would be around 296 Kelvin. So if we try to get the value of Cp at this particular value, the Cp would be around 4,181 joule per kilogram per Kelvin. So this would be the Cp value. So you need to refer to the steam table or the properties table. And after that, we can use this particular equation to get the value of m dot. So m dot here would be equals to Q over Cp delta TH. So you will get around, if you try to substitute all the values, you will get around 1,994 kilogram per second. So this would be the answer. Right. So for the second example, this is also a bit similar. However, I'm going to post this later on, but you can try it by yourself. So for this particular example, we are going to have a concentric heat exchanger. So this is a concentric heat exchanger where we're going to see that water here is flowing inside of the inner tube, while the outer tube is actually steam. So this is a counter flow, so that we are going to have opposite flow direction. So this is water and this is steam. So what happened if you try to draw the temperature graph, you will see something like this. So this would be from 15 degrees centigrade to 60. So this is water, and this is steam. So steam would be the condensing stream. So it would be at T115 degrees Celsius. So this would be your temperature graph, and this T1, delta T1, and delta T2. And this is quite straightforward actually, even though it looks quite hard. So the first one, the thing that you need to calculate would be the value of Q. So Q here is equals to delta m dot times Cp times delta Tc. So the cold side, we wanted to know the value of Q. So here the m dot has already been given. This is m dot for the cold stream, and Cp here would be the Cp of cold side. So Cp, we need to know what is the mean temperature for the cold side, which is 15 plus 60 over 2, which is 37.5 degrees centigrade. So the Cp would be around 4,180 joule per kilogram per Kelvin. So this would be the Cp. So you just substitute everything into here. So delta Tc would be here, 60 minus 15 degrees Celsius, and you will get around 13.82 times 10 to the power of 3 watts. So this would be the value of Q, the heat, that's the heat temperature. And then you're going to calculate the value of delta TLM. So you will try to calculate this. It's quite straightforward. So you will get around 75.3 degrees Celsius. Or it would be around 75.3 Kelvin. It's the same. So from there, you will know that in order for you to get the value of Q, it would be UA delta TLM. And since this is a concentric value, you also need to calculate the value of F. So later on, you will get the value of L. So this is U pi dl F delta T Lm. So L is actually the value of Q over U pi d. So this is the inner tube, inner diameter, times F delta T Lm. So you will get the value. I'm going to pause the schematic later on, but I wanted you to try it by yourself. So is there any question before we stop? It's already, 1 minute to 11. Oh, it's already 11 o'clock. So I think that's it for today. Because I know that you have your other. Did I present just now or anyone?
Yes, Doctor, you just resumed just now.
Oh, that's good. That's good, because I thought that I was talking to myself. Okay, so I think that's it for today. I will post you the schematic soon, and please take care and have a good day. Okay, see you. Bye bye.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.